El Instituto Geofísico de la Escuela Politécnica Nacional les da la más cordial bienvenida a todos los asistentes que nos acompañan en la charla científica Sistemas de Alerta Temprana para Terremotos y Tsunamis con Datos GNSS, a cargo del Dr. Brendan Crowell. Saludamos a las autoridades de las instituciones amigas que nos acompañan en este evento, investigadores profesionales del monitoreo ambiental y todos quienes están comprometidos con la gestión del riesgo. Asimismo, saludamos al público virtual que están conectados a través de las redes sociales del Instituto Geofísico en esta transmisión en vivo. Sean todos ustedes bienvenidos. Para iniciar este evento, invitamos al doctor Mario Ruiz, director del Instituto Geofísico, quien brindará palabras de bienvenida.
Muy buenos días a todos. Para el Instituto Geofísico es muy placentero el tenerles a ustedes aquí, ¿no? Pero porque creemos que es un momento importante. El Instituto Geofísico está asumiendo sus responsabilidades de monitorear y de estudiar la actividad sísmica y volcánica en el país y creemos que la forma adecuada de asumir este monitoreo es basándonos siempre en la ciencia, basándonos siempre en la innovación, ¿no? Tratando de ofrecer las mejores herramientas para que este monitoreo sea el más adecuado. Como una de las actividades muy importantes del monitoreo ahora son los sistemas de alerta temprana, ¿no? Y en este caso estamos trabajando en sistemas de alerta temprana que nos permitan dar avisos oportunos para un caso de una crisis volcánica, ¿no? Pero también sistemas de alerta temprana que nos permitan invertir, digamos, dar un aviso adecuado en el caso de la ocurrencia de un evento sísmico. Debemos tomar en cuenta de que somos un país donde la eventualidad de un sismo es algo que está presente, ¿no? Si vemos la historia, son 40 veces en las que nuestro país ha sido sacudido con intensidades iguales o mayores que 8. Eso nos daría una recurrencia de quizás una vez cada 12 años en los cuales nuestro país sufre daños fuertes causados por sismos. Entonces, es una obligación de nosotros estar preparados. Más que nada tomando en cuenta de que el país crece, las ciudades crecen, pero concomitantemente con esto, lamentablemente también crecen nuestras vulnerabilidades. Entonces, el Instituto Geofísico asume la responsabilidad de ofrecerle al país unas condiciones mejores, el trabajar en fomentar las capacidades para dar estos avisos tempranos, y para esto tenemos el gusto de tener ahora esta charla con el doctor Brandon Crowell, ¿no? Quiero solamente reiterarles nuestra disposición a seguir trabajando con el sentido de dar un servicio a la comunidad, ¿no? Y también reiterarles el agradecimiento por haber acogido nuestra invitación y estar aquí presentes en esta charla. Muchas gracias.
Muchísimas gracias por sus palabras, doctor Ruiz. Y de igual forma queremos presentar a la magíster Patricia Motes, jefa de vulcanología del Instituto Geofísico. Realizará una breve introducción del científico destacando al doctor Brendan Crowell. Bienvenida, doctora.
Buenos días a todos. Es un tremendo gusto que veo tantos caras aquí y tal vez vienen más durante la charla. Brendan Crowell realmente está aquí debido a una Fulbright Specialist Program por aquí de Fulbright, Ecuador. La jefa y también la Karen están aquí en representante de Fulbright. Brendan graduó de la Universidad de California en San Diego y empezó en el Scripps Institute de Oceanography con un grado en geofísica. Y realmente ha vivido estos 15 años después de graduarse sumamente metido en la geofísica. Y vio cuando estaba trabajando en su doctorado que no estamos acogiendo tanto o entendiendo tanto el poder de los datos de GPS o GNSS, como queremos decir. Voy a explicar, pero generalmente nosotros dijimos aquí GPS. Y el poder que voy a hablar es que las estaciones sísmicas se van afuera de escala durante un gran terremoto, mientras los GPS en tiempo real ya se sigue registrando y es posible de tener adentro de pocos minutos o segundos de cuánto es el desplazamiento. El desplazamiento del suelo se debe a la fuerza o la magnitud del terremoto. Entonces, Brendan está aquí para trabajar con nosotros en nuestra red de GPS de tiempo real y ha instalado un programa, se llama GFAST, que él mismo desarrolló como parte de su doctorado y que en los últimos 10 años ha sido trabajando en la Pacific Northwest Seismic Laboratorio, donde ya ha desarrollado más y más este programa GFAST y últimamente ha ido al Ohio State University en Columbus, Ohio, donde es profesor actualmente. Entonces, estamos muy gustosos tenerle aquí porque ya está instalado este programa que es súper complicado, pero estamos deseosos tal vez en el futuro si fuera de registrar un gran terremoto, que ya va a estar ya modulado por este programa. Entonces, con este se presenta Brendan, que está aquí hasta el lunes próximo y que realmente es su primera vez aquí en Quito, pero sí hemos tenido otras reuniones antes de pero la verdad ha sido un gran placer que pueda estar aquí con nosotros. Muchas gracias.
Gracias, Magíster Patricia Motes, por compartir esta valiosa presentación. Con esto queremos invitar al doctor Brendan Crowell, experto internacional en geodesia y monitoreo sísmico de la Universidad Estatal de Ohio en Estados Unidos. Él abordará su charla científica sobre sistemas de alerta temprana para terremotos y tsunamis con datos GNSS. Bienvenido, doctor.
Just gonna get this. I speak rather loud, so for the online presence. Excellent. Perfect. All right. Yeah. So thanks everyone for coming today. It's been a great honor to come here and work with Instituto Geofísica on this amazing problem. If you go back historically, the sixth largest earthquake in recorded history was in Ecuador. I think it was 100 years ago. Wait. So 1906, yes. So 120 years ago. And a repeat of that event would obviously be very devastating for ground motions, also for the tsunami impacts for both Ecuador and Colombia and other nations nearby. And so, the goal of coming here is to install the program GFAST and get it to work within the system here. And so, I've had a lot of success working with the folks here, getting things running, and hopefully over the next 2 days, we'll have some tangible results. And hopefully there isn't a big earthquake, but if there is, this will be useful. So I put most of the slides in Spanish, but I'm going to speak in English, obviously. So hopefully I don't get lost in this. And this will be a little bit of a history of real-time GNSS for early warning purposes, with a little bit of what's next coming up. All right, so just to start, there's a few papers that have come out in the last year that are very good overviews. I wrote a book chapter, the top one there, in this book called GNSS Monitoring of the Terrestrial Environment. And it's all on this topic. So, if you read this paper, it tries to lay it out in layman's terms, exactly how everything came to be. The second paper, it's a very dense paper in BSSA, led by Jessica Murray at the USGS. And that paper is all on the how the sausage is made for earthquake early warning with GNSS. And I guess I should also start by saying that GNSS is the generic term for GPS or navigation systems. So if you're not familiar with that term, I use them interchangeably, but GNSS it just encompasses all of the constellations around the globe, and GPS is the United States system. So since April of 2024, my program GFAST has been live in the Shake Alert system. The Shake Alert system is a United States earthquake early warning system. So it's designed to give warnings of, seconds to minutes for ground shaking. And, for using GNSS, it's most useful for very large earthquakes, but it can also be used for moderate magnitude, magnitude 7 earthquakes that would occur on the San Andreas or occur on some of the large strike slip faults throughout California. So we have not had an alert that's used GFAST so far because the magnitudes have all been too low. But in the next couple of years, it may end up contributing to an actionable warning. All right, so what's the motivation for why we want to use GNSS? This is an example from the Tohoku-oki earthquake in Japan in 2011. And on the right-hand side is the magnitude estimate for their earthquake early warning system from the JMA, Japan Meteorological Agency. And as you can see, it warned, it came up with a magnitude 7.2 or something like that in 20 seconds. And then it slowly increases to magnitude 8, where it stops. So at 2 minutes, it's stuck at magnitude 8. We all know that this is a magnitude 9 earthquake, but in a sense, the earthquake early warning system works. It detected the earthquake, so it's not anything bad against Japan here. But if you look at the warning given, that's on the lower left-hand side. Oh yeah, I should just point. I don't have a pointer. This side, this is the warning that would have been given. So this is their predicted ground motions. Red is the strongest ground motions. And in Tokyo, down here, there is no warning. If you look at what happened afterwards, so after you've recorded everything for minutes and look at the peak ground motions on all the instruments, this is the sort of motions that were observed. So there's a large amount of the population that's not warned because this magnitude only reached up to magnitude 8 here. So that was the ground motions. If you go to the tsunami, it's a much worse story. And so this is the 2-minute warning or 3-minute warning that came out of JMA. And it's color coded by the amount of, it's basically thresholded. So greater than 3 meters, greater than 1 meter, greater than 20 centimeters. And so that's how it's color coded. And tsunami warnings are given on a sort of regional basis. So for a specific county or prefecture, that's how a warning would be given out based on the peak motions, the peak tsunami motions. And, this is, while there's a tsunami predicted across the entire coast, compared to the final result, that's, many days later, after they've recorded everything and gone out in the field to discover how much of a tsunami there was, you see that most of the eastern coast of Japan is in that red or orange color. And so that indicates that they had greater than 1 meter. Some areas, it's greater than 4 meters of tsunami wave height. There's some spectacular videos online. And yes, over 10,000 people died in that near field. Could they have been saved if they received a better warning? I don't know. It's hard to say because it was very quick and very devastating. But the goal is to attempt to save as many of those people as possible. So where did the motivation for using GNSS really come from? So if you go back to 2004, the Indian Ocean tsunami, this caused widespread impacts all around the Indian Ocean. The earthquake starts here by Banda Aceh, ruptures north for 1,200 kilometers, and set off a very devastating tsunami wave. I mean, this is showing the maximum wave heights. I don't know if I believe that it went 57 feet or 17 meters, but that's what they claim in this figure here. This is from NOAA. And, you know, the near field coast, most of the land there, it's all small islands. It was completely overtopped. So waves go across the entire islands. There's possibly no way of saving those folks. But in the far field, say like Sri Lanka, India, even as far as the Comoros or Seychelles over here, you know, there were deaths from this earthquake and tsunami. So Sri Lanka saw very, very large death tolls for this earthquake. And if you go to what the Pacific Tsunami Warning Center did during this earthquake, so PTWC's Pacific Tsunami Warning Center, you know, at the time, there was no way for them to disseminate alerts in the Indian Ocean. The Indian Ocean fell out of the really the operational jurisdiction of the Pacific Tsunami Warning Center, which is in Hawaii. But they still modeled the earthquake because they model any earthquake that's global. And this is the timeline of what they came up with during the event. So they have an initial observatory message of magnitude 8.0 at 11 minutes. At 15 minutes, they issue a bulletin. So this would be any government can obtain this bulletin. And so they say it's a magnitude 8 at 15 minutes. This is a 9.2. So there's over 30 times more energy than a magnitude 8. At 65 minutes, they update this to a magnitude 8.5. And that's where it stays for several days. So they didn't know it was a magnitude 9.2 until they really got on the ground and figured out how much damage there was, looked at global observations of the earthquake. So using techniques that measure the normal modes of the Earth. Not until then could they actually say how big this earthquake was. And so, you know, an hour in, this is how fast the tsunami propagated here. These are in 1 hour increments. This is 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. You know, if you were able to say that this was a magnitude 9.2 in an hour or 15 minutes, you know, realistically, you could do this much faster. You could potentially give a warning to the folks in India, Sri Lanka, even into Thailand, which was probably about an hour for their arrivals over there. And there were significant deaths in Thailand. Now, you know, why do they underestimate their magnitude? You know, it's really just a limitation of near field seismology is really what it comes down to. So right now, the gold standard for very fast magnitudes that's done by the Tsunami Warning Centers is called MWP. And this is looking at the growth rate of P waves on a seismometer. And, you know, this is their estimate of magnitude. So this is the MWP magnitude versus the final true moment magnitude of an earthquake. And you see for magnitude 6, 7s, 8s, it's more or less a 1-to-1 line. It does pretty okay. And then as you go higher up to the magnitude 9s, it saturates. And it really comes down to, if you go back to theoretical seismology, the body wave magnitude or the surface wave magnitude have a limitation, you know, where they can record certain magnitude earthquakes in the near field. Now, for the real magnitude, what's often used is called the W phase. So this is what the you know, global, the National Earthquake Information Center at the USGS uses to determine the large magnitude moment tensors. And for this, there's a limitation in how close you can be to the source. It's somewhere between 8 and 10 degrees from the source, because what you need is the P and S waves to separate to be able to record the W phase. So for the W phase, it does really well at getting the magnitude, but you know, these first messages are coming out at 10 minutes for just an initial magnitude estimation, more like 20 minutes for a true W phase magnitude. So, you know, in that regard, it's limited. Like, you can't really warn people in the near field of that magnitude earthquake because it's going to take 10 to 20 minutes to get that solution. And, you know, the PTWC has been doing a good job at reducing their warning times. So back in 2004, this is Sumatra, this big circle here, and Tohoku right here. They've come down from 20, 30 minutes all the way down to maybe 5 or 10 minutes for their first messages. But you notice that these very, very large ones are always underestimated by upwards of a magnitude unit, if not more. And so that's really what we're trying to solve here. All right, so just to kind of summarize those previous slides, for tsunami warning, MWP is kind of that first solution that's available in less than 10 minutes, but your magnitude saturation could potentially be large for magnitude 9 earthquakes. Those W phase solutions, and for the theoretical seismologists in the room, it's a higher mode Rayleigh wave between P and S wave. They don't show saturation, but they take much longer than 10 minutes usually. And then for earthquake early warning purposes, so this is where you're basically trying to warn of shaking prior to having the shaking arrive at your location. The P wave methods are effectively body wave magnitude methodologies. So they look at the peak displacement of a few seconds of P wave, and those basically will get to 7.5. And after that, your sensor is going to record the same amount of motion for a 7.5, an 8, a 9 at the P wave. You have to start including much larger surface waves and shear waves and other sorts of waves to really get at that magnitude. All right, so why do we utilize GNSS? GNSS is really a non-saturating estimate of ground motion. The motion is recorded with respect to the center of the Earth. So you have satellites that are positioned with respect to the center of the Earth. And technically, this is in a non-inertial reference frame if you put it with respect to the celestial reference frame. So in a sense, you're able to record the absolute motions in space of a point on the Earth. Why is this important? What happens is you can record the body forces of an earthquake. So the actual motion of an earthquake moving is what's known as a body force. And in traditional seismology, you can't record the body forces because your seismometer in the near field doesn't know where it is in space. So you could move it, 5 meters over here. It has no idea that it's over here. You can try to estimate that, but in essence, that's a limitation of the sensor itself. It records very nicely the motions, the shaking, but it's not going to record its absolute motion in space, which does not allow you to get at the body force term. Okay, so after the Sumatra earthquake, a couple of papers started to come out, and here's a paper by Jeff Blewett that was taking what's called 30-second sample rate GNSS. So there's many different sample rate data, and they took 15 minutes of data at 30-second sample rate, and then they just estimated offsets of these sensors. And there weren't many stations at this time. This is 9 stations or 10 stations, and this is out to maybe 2,000 kilometers from the source. So this was all of the stations available at the time. 2004 was pretty much the start of this sort of method. But they said that, within 15 minutes, you could say this was a magnitude 8.9 to 9.1, just off of these offsets that were recorded within 2,000 kilometers. So if you go back to, what the PTWC did, it was a magnitude 8.5 at 60 minutes, but it was at an 8.0 within 15 minutes. So it's a one magnitude unit difference already. So then a few years later, I wrote this paper, and it's basically looking at the dynamics of the wave field and seeing how quickly you could produce a source of suite of products to say what's the magnitude and style of rupture of an earthquake. So at the time, I don't know how familiar people are with GPS processing, but there's generally 2 modes. There's relative positioning. This is kind of what surveyors do, where they have a base station and a reference and rover station, and you do relative positions between that. And that's what's shown here. So at the time, you couldn't do what's called precise point positioning very well because the corrections from satellites weren't very good. So we were stuck doing relative positions. This is for the Tohoku-oki earthquake in 2003. We triangulated the entire network, and then we plot here the strain that as it's propagating across the network every second. I can just play that again, just so in case you missed it. But the nice thing here is that you're seeing both the dynamics of the wave field move across, and it's moving across the entire network. These are fairly large strains here. And then you start to see permanent strains that are caused by internal deformation of these triangles. And so both of those pieces of information can be used. You can use the dynamics of the wave field and also the permanent deformation that's occurred due to the earthquake. All right, so how do we use GNSS data in real time? So the first thing, we looked at the peak ground displacements. So this is a waveform for an earthquake in Alaska, the northeast and up components. And it's as easy as it sounds. You just look at the peak motions that are recorded at a sensor, and then you can relate that to magnitude. The next thing would be to take those co-seismic offsets. So these are the permanent offsets of an earthquake. And from that, you can get things like the moment tensor of an earthquake. You can invert for slip on the fault. You can get the magnitude as well. And then we take this information and then we project out into the future what's going to happen. So, for that, you can project out the ground motions of an earthquake. Also, what's the inundation of the tsunami itself? So peak ground displacement scaling is fairly simple. It's a log-log relationship between the peak motion recorded at a station, its distance from the source, and the magnitude of the earthquake. And, at a given distance, these are all at 100 kilometers for different magnitude earthquakes, 9.1, 8.8, 8.1, and 7.2. You see that it's going up in peak ground displacement. That's really all it's trying to say. And so we've come up with an actual scaling law for this. This is the first one that was developed from only a few earthquakes. This is a magnitude 9, 8.3, 7.2, and a couple of mid-5 earthquakes that we recorded. And we've added now somewhere like 60 earthquakes to this data set, and we keep finding very similar results. In this paper in 2015, we showed how you could use this. So if you basically have a travel time mass that's expanding, you can incorporate stations at a given time and then estimate the magnitude from that set of stations. And the important thing here is you can estimate the true magnitude of an earthquake when you're about halfway through the earthquake itself, halfway to 2/3 of the way through the earthquake. This is for Tohoku. You get up to magnitude 9 in about 2 minutes. And then just a bunch of other earthquakes here that are lower magnitude. So I just want to show what this would look like during Tohoku. So you'll see 3 sets of dots appear. You have the map view over here. This is a log plot of the displacement versus distance, and then the magnitude estimate that's coming out of GFAST. So, we're incorporating stations. This is showing the bound of the stations we're incorporating. That's due to that travel time mask. And then we invert for a single magnitude value up here. And you can just see how that scales in space. So, it grows quite a bit. The first estimates are around a high 7, about 50 seconds, but then it quickly grows up to a magnitude 9 by 2 minutes. So from there, we can take the co-seismic offsets and estimate what's called the moment tensor. And the moment tensor is really just giving you which fault slipped. So it'll give you 2 faults. It'll give you ones that are perpendicular to each other. And so from there, we can actually say which fault actually ruptured or have some idea of which one ruptured. So these are some videos of the El Mayor Cucupa earthquake in Mexico. And you see the vectors are getting, growing over time. And then the estimate of the moment tensor is down here. We didn't have the true moment tensor on here, but it's a strike slip earthquake. This is what it should be right here. And then for that Tohoku-oki example that I showed a few slides ago, you'll see those vectors start to increase in size. And this is our estimate of the moment tensor versus what's the final moment tensor. So reading moment tensors is a little strange, but you just want these two to be roughly the same looking here. All right, so then from that point, we take those two fault planes and we create two actual faults. And you can invert the exact same displacements onto the fault to determine how much slip there was. So this is those same two earthquakes. This is a paper in 2012, and you'll see those vectors start to come up. And then the slip model for this earthquake, this one's about 2 meters, 2 to 3 meters of slip. For the Tohoku-oki earthquake, it gets upwards of 4 to 5 meters of slip. And from these models of the ruptures, it should play again. You can then properly compute what's the ground motion, or for a subduction zone earthquake like this, you can compute the tsunami that would occur due to this earthquake. All right, so I just wanted to show, what are the constituent components of an early warning system. And here at the Instituto, they are performing basically all of these things here. Where you have data in the field. So these are stations that are installed. You have raw data coming from those stations. You have some way of getting the data back called telemetry, it's coming over cell phones or Ethernet or other methodologies. Then you process your data. So you say, what was there an earthquake? What's the P wave? What's the arrival time? All that stuff. Then you take that sort of information and you determine a solution that would be, what's the magnitude of this earthquake? What are the, location of this earthquake? Information like that. From there, you would estimate the impacts of this earthquake, so the ground motion or the tsunami, and then you alert the public. And so the public alerting is very complicated. This requires a lot of coordination among the government to do this, because you're sending out mass alerts to many people over cell phones, over radio, TV. So it's not something that's very easy to do. It's probably the hardest part of the entire early warning system. So to get into the GFAST system, so those slides that I showed on the peak ground displacement scaling, the CMT, the finite fault, those are all, those are scientific studies that I performed when I was a graduate student that then become part of GFAST. So they're all part here. But really, this is an iteration of the previous figure, where we have, data coming from stations in the field to some processing center. It comes to our system, and then we basically have a continuous buffer of data in our system. And then we have a seismic system that's sending us alerts. It'll send us, hey, there was an earthquake at this location at this time. And then from there, we decide if we want to model the earthquake. We use those modeling modules, and then we basically send this information to different agencies. So, if you go to the tsunami warning centers, or it goes back into Shake Alert and contributes to the new warnings that are going out. Just to show, we've done a lot of testing of GFAST in the Shake Alert system. This is the Tohoku earthquake right here. So you kind of saw that on that video. It's the same sort of magnitude evolution of that earthquake. And really what we're trying to show is that if you include the GNSS for these types of earthquakes, for these subduction zone earthquakes, you can increase the amount of land that's warned, which in essence, you're warning more people over time. All right, so for the earthquake side of things, we have a bunch of earthquakes we can look at, but we don't have a lot of very large magnitude tsunamis to look at. So there's only a couple around the world. We're mainly concerned with the west coast of the United States, the Cascadia region. And so we create fake earthquakes from this to test our system. So this is just a series of different fake earthquake scenarios that we've developed. They're based off of coupling models. This is saying how much the subduction zone is locked. And then we can generate these sorts of earthquakes very efficiently and basically determine what the seismometers would see and what the GPS stations would see for these types of earthquakes. Then you take that information, you see how well you could do in real time. So we also would take that same model and we can forward model the tsunami. That this is actually, while it's a complicated problem, the equations are what's known as hyperbolic equations, but they're solvable in a forward sense. So this is just taking those same models and looking at what the inundation is at a number of key locations along the West Coast. And you see these are all magnitude 9 earthquakes, but there's very different impacts along the coast. And so that's information that we want to be able to leverage. We want to be able to model all of these types of the earthquakes so we can give this better scale warning to the public. And so, in GFAST, we just take those simulations. This is a simulation of a smaller magnitude earthquake. I think this is maybe an 8.3 or so. And this would be the vertical deformation on the seafloor, which is what's going to drive a tsunami in essence. And then we have what GFAST would produce and what its vertical deformation on the seafloor looks like. So we take this information and then we try to compare them. This is going to have a certain tsunami and this will have a tsunami associated with it. We can difference the tsunamis to figure out how well we're doing. So just to give a sense of what those tsunami models look like, this is for that, synthetic earthquake. We call it fake quake source. This is what GFAST would do for that same earthquake. This isn't very satisfying. This map view doesn't look great, but we can put this into a simpler form. So, we have the true max tide gauge recordings. So we make fake tide gauges all along the coast. And then we have what GFAST would do. And, for the most part, we're able to do very well at predicting the tsunamis from a pretty simple earthquake source. And these numbers down here just indicate what sort of percentage difference we are. So roughly, we're overestimating the tsunami impacts at 120%. So it's a little bit greater than what you would observe, but in essence, you want to probably be a little conservative with these types of estimates because there's going to be areas that are harder to model. And so you want to kind of overestimate just a little bit for tsunami warnings. So there's some additional considerations for using GNSS. Seismometers are very precise and accurate. Well, they're precise. They're able to measure down to microns of motion. They don't measure very, very large motions well, but they measure small motions very well. And they can record smaller to moderate size earthquakes very well. Now for GNSS, we have what's called colored noise, where at certain periods, as you're getting longer and longer periods, the atmosphere is changing. And also you have issues with the orbits are changing. So you have this increase in noise. This is what's called a probabilistic power spectrum. Really just what matters is if you see these horizontal lines, that would be a white noise level. So this one's 0.1 centimeters. This is 1 centimeter, 5 centimeters, 10 centimeters here. So at very high frequency, less than 10-second period, you're in the sub-centimeter range for noise. The vertical is about a factor of 2 to 5 worse. But then as you go out, this gets larger. So this is something that we have to consider when we're doing warning systems, is that while it's good at recording large earthquakes, our noise is getting worse over time. And so in the shake alert system, if you do end up reading this paper, all the logic and how we do that and incorporate it into shake alert is in there. All right, so I'm just going to talk about a few projects on the horizon here. So one thing that I've been working quite a bit on is what's called a GNSS velocity data center. This is turning GNSS stations into velocity sensors, so like seismometers. And there's a lot of different uses for this data, including an early warning. And then we have a large project where we're doing tsunami loss estimation. So if you can model the tsunami very well in a few minutes, theoretically, you can model how many people are impacted, what are the financial losses of this system or of this earthquake. And so if people are familiar with the pager alert system for earthquake ground shaking, this is the same thing. This is for the tsunami impacts. So for the Velocity Data Center, it's a project funded by NASA, and I'm working with EarthScope on. What a GNSS velocity is, it's a time difference in the orbits and a time difference in the phase. So when you do that, instead of displacement, you get velocity. You also get rid of all of the air sources in GNSS. So you're able to record much smaller earthquakes doing this method. I'm not going to go obviously into all that, but it's important to understand what it is. You also can get at the total electron content. So for space weather purposes or monitoring terrestrial events in the ionosphere, it's very important. A lot of folks are very interested in that part of it. So we're building a whole bunch of ways to access this data. Right now, we'll basically be broadcasting this out over a message broker for people to listen to. And then we're basically looking at all the standard ways you can model earthquakes. So the standard seismic techniques, like create a shake map, like we're looking at how you can use this data for that. W phase inversion. One of my students is doing W and phase inversions with this data, which you can actually reduce your distance for. And I just want to show a few examples of like very large ground motions recorded with this. So for those that are seismologists, for recording velocity, you need a broadband. I mean, you can integrate your accelerations to velocity, but you might have drifts in the system. This is not filtered in any way. The Kaikoura earthquake, you have the displacement in the black here, and then the red is the velocity. So it's getting upwards of 1 meter per second. This is very large ground motion. The Norcia earthquake in Italy in 2016 is a 6.6. This gets over 1 meter of motion. And then the Nepal earthquake also in 2014. This is one station, and it's recording out to 2,000 seconds. You see there's another earthquake. So this is the main shock and an aftershock. So it recorded both of them. In between, there's no noise issues whatsoever. It's able to just crank along, and it's basically recording zero values in between. I mean, the noise is there, but it's still doing very well here. This is an example I show a very extreme case. There was a magnitude 5.4 earthquake in the middle of a lake in New Zealand, so Lake Taupo, this is known as. So earthquakes here, they have this station on top of this wooden platform in the middle of the lake, right there. And it hits 3.3 meters per second. And it actually is going over 1 meter per second for quite a while, for like 20, 30 seconds. Now, people don't generally know what 1 meter per second feels like. That's really bad shaking. Like, you definitely can't stand. 3.3, you'll be thrown off of this into the lake. Like, that is a large amount of ground motion. I'm surprised this thing's still standing after that. This is all side effects. This is not, the earthquake did not generate 3.3 meters per second. This is, wood into mud, and it's just a lot of shaking just due to the poor build of the station. So to use these ground velocity observations, we've actually come up with a new version of the scaling law. So this is the original scaling law for PGD. These A, B, and C are just coefficients we find looking at old data. And this is the distance to the source, which is usually hypocentral distance. And Now we came up with a law for the PGVs looking at like true distance to the source. So we have a different R value, and we have a higher order ground motion model. But the thinking is you could take this, what's called R proxy, and put it into there. And so you can actually do the scaling without a distance to the source. You allow the PGV to modulate your distance. And this is an example of how that works. This is for Kaikoura, and it ruptures from here to here. And the squares, which are probably hard to see on this screen, they're all up here. So the squares mean that it reduced the distance to the source because the motion is directed at these stations, but also the rupture is like this whole distance. So the hypocentral distance is here, but your true distances are all the way up to here. So this is all reducing the distance, so making these stations closer to the source. If you go in the other direction, they're all circles, so they're positive, so they're making the stations further from the source. And that's really like our way of thinking about this model. And we've looked at basically 2,000 observations, and the point of these histograms is this is how the original scaling law would work. This is just two different distance metrics. And it's much more broad across the histogram. And we separate it into magnitude 7.5 or greater or less than 7.5 here. When you use this distance proxy, you see how much more peaked these distributions are, both for greater than 7.5 and for less than 7.5, the original law does okay. But it's still a bit of an improvement. So, we want to use this to improve our estimates of ground motion during an earthquake. So force shake alert, that's our main goal. And you also can reduce the dependence on a location of the source. So it could perform without knowing where the earthquake actually occurred. All right, so just going to show a little bit on the tsunami loss stuff that I had mentioned. I showed those simulations we did. That's a big part of this. So I'm not going to show it again, but it's a big project with University of Oregon, Tohoku University, and a company called ImageCat that does risk and loss estimation work. And so for this project, you're not supposed to be able to read this. It's just supposed to show that we're doing complicated things, and you're supposed to believe us that we're doing complicated things. And so, it's 6 different work packages. We have the source models, which I've showed. So you take the source models, you create a tsunami. Then we have some sort of impact analysis. So, determining how much loss there is, basically where is the tsunami going? And then we can forecast our different impacts. So we can do this probabilistically. We can do single station based. We can also do this in real time. We're building a platform, which I don't have any screenshots of, but I have a wireframe that we've made, and it should be getting released in the next year to the public. It's pretty cool. Then we've been doing a lot of validation, pilot studies with different stakeholders and working groups. And then, trying to work with end users for engagement. All right, so I'm just going to talk about the part 2. This is the analysis of the impacts. And for this, we have all this information. This is the city of Long Beach in Washington, United States. And so we have things like the census block populations, the inundation hazard at 0 meters, at 2 meters, all these sort of GIS layers for looking at information. From that, we can estimate things like what's the distribution of structural and content damages by different flow depths. So in this case, the structural damages in the blue, contents damages in the orange. The bimodal distribution, I think, is due to the fact that the geography is such that if you get above a certain point, you actually then start to hit a new section of land here. But this is obviously a very devastating event for a sparsely populated area, actually. Only like 10,000 people live here. From there, we can look at things like the evacuation times versus the tsunami arrival times. And then we can look at things like the casualties. So injuries and fatalities here. Obviously this is a pretty, out of the total populations here in the yellow. So, most people are injured in this scenario. Just because this is one where you have to get all the way over here to be safe. So anyone that's down in this zone, it takes like an hour to 2 hours to walk up there. And by then the tsunami would have hit. We can obviously do the financial losses from those buildings and the population exposure, and also the downtime. So different assets being down, like power and water, et cetera. And this is an event where, basically somewhere around you have $7 billion of exposure, but over $6 billion of losses in this case. So it's basically almost total damage in this case. And then the rates of fatalities are based on this pedestrian evacuation time chart, and this is your sort of probability of being injured or having a fatality as a function of the speed at which you're walking. So if you're really fast or slow, those matter for evacuations. Yeah. The what valley? Wait. Structural damage. Yeah. Okay, so structural damage is based off of databases. So there's a global database that Microsoft does, but in the US, there's generally FEMA has the HAZIS database. There's also some other databases of structures that are done by the states themselves. So we're trying to use any of those. Like the way we're building our platform, which I ended up on this page, is that we would allow the user to pick which exposure model they want to use or which building inventory they want to use. So we ourselves are not trying to say this is the best one. We want the users to say, oh, we actually think this is better, so let's use this one instead. And so this is my second to last slide here, where this is just showing how we would envision these sorts of things, where you would click on a block in the map and it would give you these little maps of casualties and financial losses. And in this case, it's probabilistic because we're using a suite of events and there's a lot of logic that goes into that. You'd also have the same thing for single events. That's a little easier to display because you can model that out much easier. It's probabilistic, you need to understand a lot more about the occurrence and recurrence of different earthquakes. All right, so just in conclusion, the GNSS data does not saturate for these largest earthquakes. And the displacement is really diagnostic of the total moment release in an earthquake, which is why it does not saturate. For enhanced ground motion and tsunami predictions, we can make these with GNSS data for useful early warnings. So for tsunami warnings in the first 10 minutes after an event, for seismic shaking within 10s to 20 seconds. And then this has been live in the Shake Alert system since March 2024. We've had a project with the Tsunami Warning Center. It's installed there, but not being used operationally right now. And we haven't had any alerts yet to date. There just hasn't been any earthquakes that are large enough in the United States to have triggered the system. So thank you.
Agradecemos la exposición del doctor Brendan Crowell y el interés de todos ustedes en esta charla. En este momento abrimos un breve espacio para preguntas del público. Les pedimos levantar la mano para que podamos acercarles el micrófono.
Brendan, thanks for your talk. We know that if we have a seismometer which measures velocity, we can integrate it and get a displacement, right? And I understand that is in the far field, the soil is the ground is going to behave elastically, and you can get a right displacement in that case. The problem is in the near field, as you told, And my question is, how much is the distance to consider near field, which depends size of the fault and magnitude?
Got it. Yeah, so the question is, where does the near field to far field boundary begin? For what size earthquake? And that's kind of a tough one to answer. Usually what's done is you generally say, all right, what's the size of the fault? And if you're within one wavelength of that or two wavelengths of that, so if it's 200 kilometers long, within 200 kilometers is maybe still the near field. There's not really a great definition of that because the near field term still will persist out to 1,000 kilometers. So you have to look at the decay of those terms with respect to the other terms. But for magnitude 7, I would say you're in the 100 to 200 kilometer range for near field, maybe less than that actually. And then for a 9, you're looking at 400 to 500 kilometers at least. There's permanent offsets from Tohoku into China. So it's hard to actually say where did that boundary end for large earthquakes. But as a first order, I kind of like to think about the wavelength of motion. And that's obviously going to be modulated by how much slip is on the fault.
Tal vez alguna otra pregunta.
Okay, what is the current limitation of the system and how do you expect to improve in the future? To improve.
I mean, I can talk about all right, so the current state in the United States is that what I showed is running. There's improvements that need to be made for ground motions mainly. So to better improve the prediction of ground motions in space, we need to add more logic or add in the PGV stuff that I was talking about. So that's the main limitation is that for peak ground displacement, we assume it's a point source, which is for a very large earthquake is not a great assumption, but it still works okay. So the limitation, so in terms of here, we expect to have, we're basically working with two systems. So there's a sort of a offline system where you can basically request GFAST to run. You give it event information and it'll just run and do the model there based off of the data that's in the database here. So an analyst could do that. And then there's the real-time system, which is written in C programming language. And that requires an automated trigger. So for here, what we've been working on is size comp, using the automated triggers from size comp for that. But it might be important in the future to add in a true early warning system, a seismic early warning system for those triggers, because size comp really wasn't built for that purpose. It does okay, but it's not designed for that optimal speed. The other limitation here is the number of stations. So there's only so many stations that are real time. I think right now it's 6, 7 stations or 10. Okay. But not all of them are running all the time because there's just issues with the telemetry or the location of the station and being able to get out to it and fix it. So the density of stations certainly needs to increase, both in the seismic, maybe not so much, but probably still in the seismic and then also in the GNSS. The other thing, most of those real time are on the coast, and that kind of ignores here. So, there's all the volcanoes you could do stuff with. I'm not even dealing with volcanoes here, but the same concepts of how you deal with data, how you would model the volcanic eruptions could be used. It's a little bit of a different problem. But then there's also the larger fault zones in this area. So that's an area where obviously the ground motion would be very large and the impacts would be very devastating. there's no tsunami from that, but it's still, I think, a blind spot right now.
¿Alguna otra pregunta? Bueno, entonces, muchísimas gracias por sus preguntas y aportes. ¿Qué?
Short one. How long will take to install the program for Ecuador?
So the first version of it, the Python version, it's on GitHub now. And so after lunch, we'll make sure that works. I mean, I've had it working on my laptop, so I know it will work, but there's still some things we want to make sure, do some troubleshooting. There's also a little bit of development still on like how you visualize the data and make sure it's useful to the people that are doing things with the information. And then the C version, I think there's still some dependency issues to deal with because they're installed on different operating systems. So it's just a matter of fixing those issues, but then also fixing the triggering of the system. So I know Wilson built a message broker for this, but it's, we need to test that. We need to make sure that message broker from size comp to GFAST actually works.
First off, thank you for the presentation. It was a very nice presentation. And my question is, you mentioned that we have only 10 stations here with real-time transmission, right? So what is the minimum number of stations that you need for your program to run? And the other question is, you have shown us like examples from Japan and from the US, but we are certainly not at that level. So is there any suggestions for us to follow to work in a much better this? Okay, thanks.
So right now the minimum number of stations is set at 4, but that's kind of arbitrary. We could go lower. It's just there's more uncertainty with what you're doing going lower. We kept that because of the standard for seismology where you have 4 unknowns. You have the location of the earthquake X, Y, Z, and T. So we kept it at 4 just because of that. I should have shown the example from Pedernales. There were a lot more stations because a lot of those stations, they were downloaded and then processed after the fact. So they weren't real time, but something like 15 to 20 stations for that. And it does very well for that. Like that's the example that we're kind of using to test right now. In terms of, where to add stations, so right now, since it's very linear where all the stations are, there's curvature to the coast, so you get some depth, but what you really want is to get sort of the second layer of stations. So you can look at the attenuation of motion across the stations, because that's effectively what's happening with the PGD relationship is you have attenuation that you're modeling in addition to the max displacement. So if you can get sort of a second layer, maybe 50 kilometers inland, I know the geography is a little tougher due to the mountains, but that would certainly help, is to have a kind of a second layer of stations.
Bueno, me parece que estamos en un punto muy, muy interesante. Yo quería darles la perspectiva del Instituto Geofísico. Quería indicarles de que la red de GPS que estamos usando para este sistema no es es una red nueva que estamos construyendo justamente por iniciativa de Patty. Estamos teniendo estas estaciones y comenzamos instalándoles en los sitios que nos parece el sitio más sensible para nosotros para detectar grandes terremotos, que es en la costa norte, o sea, en la parte de Esmeraldas. ¿No? Aparte de esta red con estos instrumentos que son apropiados para para transmitir y para tener la corrección de órbitas casi en forma instantánea y en forma continua. No tenemos nuestra red, digamos que ya sería de una tecnología un poco que ya no es la adecuada para esto, que nos va a hacer, que nos sirve para hacer los cálculos, como decía, offline, ¿no? O sea, pero que no nos sirve para el sistema de alerta temprana, ¿no? Para el sistema de alerta temprana necesitamos también que todas que las estaciones tengan la capacidad de transmitir. Las estaciones de GPS nosotros no les teníamos con esa transmitiendo en tiempo real, ¿no? Entonces, gracias a y el otro tema que ustedes han oído mucho de SAISCOM, ¿no? Y también de los sistemas de necesidad de acoplarles, de SAISCOM como un disparador del mensaje para que comience a correr el programa GFAST, ¿no? Lo que quiero decirles es de que SAISCOM fuimos de los primeros, quizás el primer observatorio sismológico en América Latina que instaló SAISCOM, ¿no? Ahora es usado por casi todos los observatorios sismológicos de América Latina, pero no es el más apropiado para sistemas de alerta temprana. Entonces, quizás podríamos trabajar tratando de hacer que SAISCOM corra en una versión, corre en paralelo con otra versión que que dé el mensaje con la rapidez, lo más rápido posible, pero sin la precisión necesaria a fin de tener el disparador y de poder correr en lo más rápido este otro programa, ¿no? Entonces hay algunas soluciones que se pueden hacer, ¿no? Pero lo importante es que Brandon nos deja una tarea, ¿no? La tarea es de reforzar nuestra red de GPS, ¿no? De tener esta segunda línea de GPS, ¿no? De trabajar en el acoplamiento con seis, con otro disparador que se pueda desarrollar y poder, después la tarea más grande sería cómo, una vez que se tiene la magnitud, cómo eso puede ser incluido dentro de un aviso temprano que sea difundido a la población y que también que sea comprendido y adecuadamente, digamos, y que tenga una población que ya es capacitada y que no entre en pánico cuando reciba un mensaje de estos, ¿no? Entonces, estamos comenzando, ¿no? La idea es seguir trabajando y tener después de un tiempo, pero no tan largo, tener un sistema de alerta temprana que nos pueda ayudar como algo que salve vidas, ¿no? Que ayude a la seguridad de la comunidad, ¿no? Eso quería indicar.
¿Alguna otra duda por parte del público? ¿No? Perfecto. Bueno, agradecemos la exposición del doctor Brendan Crowell y el interés de todos ustedes en esta conferencia. Y muchísimas gracias. Antes de concluir, expresamos nuestro reconocimiento a todo el equipo del Instituto Geofísico de la Escuela Politécnica Nacional por la organización de esta actividad. Y también invitamos a la audiencia virtual a seguir nuestras redes sociales oficiales y el sitio web del Instituto Geofísico para futuras charlas y contenidos relacionados con la gestión del riesgo y el monitoreo geofísico. Con esto damos por finalizada la charla científica Sistemas de Alerta Temprana para Terremotos y Tsunamis con Datos GNSS. Les agradecemos su presencia y puntualidad. Que tengan una excelente jornada.